Okay, then let's apply our concept P-Basashita metric into a matrix algebra or in physics and quantum information theory, so-called Burse distance. Okay, before we talk about this, I will introduce some notation that I will use in the matrix algebra. Okay, first, Mn is the collection that is a complex matrix. N by n complex matrices. Collection of, okay. And Hn is a Hermitian matrix, which means that Hn explicitly Hn means that collection of complex element matrix such that M star, which means that transpose, conjugate and transport is same as the original matrix. When you think about a quantum mechanics, a Hermitian matrix very, very important. When you think about a physical quantity. In quantum mechanics, every quasical quantities means real, not a contained imaginary number. So every operation should be physical quantity or physical operation is Hermitian matrix. Okay, so in this sense, the Hermitian matrix is very important in quantum mechanics. Okay, let's see. Pn is a collection of n by n square positive semi-definite matrices. Explicitly, if we define the set is also complex element matrix X T M X is positive. In the case, the X means that like matrix, transpose matrix. So if it's written about X1, X and n by 1 matrix, so that is a Pn, and Un is a unitary matrix. Explicitly defined, that is M star M is equal to. Note that if we think about Mn is a complex matrix. So if we element in of matrix is a real number, that is On. On means that orthogonal matrix. If you see orthogonal matrix, I explained in a rigid motion or isometric motion. Every rigid motion translation, rotation and reflection is its composition, identity, inverse is contained O n. So that is related to preserve the, including the unitary matrix, that is related to preserving the distance. Okay. And TRA means that trace of A. So if n by n matrix is given, trace A means that summation of diagonal, sum of the diagonal element. Okay. Based on this, I will define definition. A matrix B is called a square root of A if the matrix product, so B, we can witness B square is A. In a number theory, if A square is equal to B, we can, and if, okay, then we can say A is square root of B. Okay, that is the background. But problem is occur if we think about this matrix. In general, in the matrix world, B is not unique. Okay. So there are many metrics to satisfy B square to A. Of course, in a number theory, we can think of a plus and minus. So this situation occurs in a matrix, but every positive semi-definite matrix, so PSD, has a unique square root. So in that case, we can write if in that case, okay, if we write, so in that case we can write B is written as like this. So that is definition and notation. Let's see the another definition, that is Frobenius inner product. That is defined a complex matrix Mn is collection of complex matrix. If we take matrix, two matrix A and B, and that means Frobenius subscription is defined by like this. If you observe this if n is 2, so A is A1 consists of this element, and we can see conjugate of A is like this. Transpose and conjugate. So that is written as like this. Okay? If transpose the matrix, diagonal component does not change the position, but that guys change a position like this and take a conjugate. So, and consider B is given. I will show that is equal to trace, that is definition, but it's essentially is trace the matrix. If we compute this matrix multiplication, and let's see a diagonal component, because we only think about, we can compute a trace. That is written as here, and that is written as here. So trace A star B is ultimately bar A11 B11. The trace means that addition of the diagonal component. So if we just write this, that and like this, like this, then we can express a sigma I and j from 1 to 2 bar A j B I j. So the Frobenius inner product written as a trace A star B. And if we think about the norm, Frobenius norm, is defined like this. Okay. Originally, that is reason, because that is Frobenius norm. Generally, the notation is F, but some people written as subscription 2, because that is related to L2 norm. In the discrete case, a small letter, small L2 norm. Okay, that is by definition, that is written as trace A star A of scale. That is written as, by definition of the Frobenius inner product, in this like this. Okay, that if bar and component is just such a complication is expressed as scale, length of the scale, and that is written as like this. Okay, so anyway, that is one of two. So in an L2 norm, when you think about continuous case, F2 is written as F square d mu and a 1 over square or half. Okay, that is a continuous case. In discrete case, integral is changed into summation. And however, everything is, except the changing an integral into a summation, everything is same. So in this, however, because that is summation, discrete case, to discriminate between these two continuous and discrete, we can use small l2, and this 2 is come to small l2 norm. Okay, so that is Frobenius norm. Okay. Okay, then based on this idea, we can define a Burse distance, our main topic. Burse distance. Let A be in Pn. That is, Pn means that positive semi-definite matrix, collection of PSD matrix. Then consider a function D such that DAB, every two positive semi-definite matrix AB is given, if defined, that is trace A, trace B, and 2 trace A square. As I said, that is uniquely determined if matrix is positive semi-definite matrix, and B and A square and square and square. It's complicated. As I said, that is a square root of A. Then the square root. Then D satisfies metric axioms. Then we call DAB a Burse distance. Okay, that is okay on this type of the distance. But interesting point is that another alternative name, a Wasserstein metric. That is interesting because as I thought in a previous lecture and this lecture, that is related to optimization and optimal transportation. So natural question, if some people, the birth distance is called Wasserstein metric, our natural question is that why birth distance is related to optimization.